Hello everyone, myself Deepak Upadhyay from Impulse Technology Gurgaon, Delhi. In this video, I will show you how to calculate the energy band of topological insulator by using NanoDCAL software. So let's get started. So this is my device studio, that is a graphical user interface for this NanoDCAL software, and this interface will help you to model the structure. You can do some modification, manipulation in your atomic structure and device structure. First, I would like to import the bismuth selenide from my local database. So for this, you can select this file option, select this import option and go to the import local. Here you can see this is the material database that exists inside this software. So you can go to the 3D material, then select novelty material, and here you can see this is the topological insulator, and here you can see bismuth selenide. So you can see this is the bismuth selenide that I have imported from my local database. So if you want to simulate the property from this structure, so you can go to the simulator, select this NanoDCAL and go to the self-consistent field calculation. Here you can see this is the SCF calculation parameter for this bismuth selenide. You can see this is the electron temperature, cutoff energy, exchange correlation, LDA, GGA. This is the K point sampling. This is the iteration control, density matrix, Hamilton matrix, total energy, and this is the basic settings, and this is the spin type, collinear spin, general spin as well. So first I would like to calculate without spin, and here you can send the K point sampling. N1 is equal to 9, N2 is also 9, N3 is equal to 3. Then you can click on this generate files. Once you click on this generate file, in the project window you can see the SCF input for this bismuth selenide has been generated. So you can select this SCF input, right click on open with, and this is the script for bismuth selenide. Here you can see what parameter we have defined. This is the basic settings, and this is the iteration control, and this is the atom and their Cartesian coordinate point. So you can select this SCF input, right click on run option, and here you can define the number of parallel cores, suppose 5 core, 10 core, 15 core. So there is no limitation of core, you can define up to 128 core. Then you can click on this run option to run this. In the bottom of the page you can see this is the job manager where the SCF input is in the running condition. So in the meantime you can select the band energy, then you can go to the simulator, select this NanoDCAL, go to the analysis. So from the property you can select any parameter, whatever parameter you want to calculate. So I would like to calculate this band structure. Here you can see this is the symmetry K point. So this is the Brillouin zone path of this band structure, and then you can click on this generate file. Similarly you can run the band structure.input file as well. You can copy this project and perform the calculation with general spin. You can rename this project spin orbit coupling GGA calculation, then you can click on OK, and you can select this project and then go to the simulator, select this NanoDCAL and go to the self-consistent field calculation, and here you can define the same K point sampling and then go to the spin type, and here you can select the general spin, and then you can copy this checkbox spin orbital interaction, and then you can click on this generate file. So similarly you can select this scf.input file for the general spin, right click run option to run this job, and then go to the simulator, select this NanoDCAL and go to the analysis. Here again you can select this band structure and then you can click on this generate file. Similarly you can run this band structure.input file, and if you want to make a surface slab of this bismuth selenide, so you can select this bismuth selenide and go to the build option, and here you can see this is the surface slab. Here you can see this is the Miller indices HKL value, and this is the element and their fractional coordinate. So I would like to select this HKL value 001, and then you can click on this build option, and again you can select this simulator, go to the NanoDCAL, and here you can select this self-consistent field calculation, and here you can define the general spin, then you can select this spin orbital interaction, and then you can click on this generate. So you can run this SCF input as well. Again you can select this simulate, go to the NanoDCAL, go to the analysis part, and here you can select this is the band structure and this is the density of state. Here you can see this is the K point sampling, and this is the number of energy point, energy range, and then you can click on this generate file. So similarly you can run this band structure.input file and density of state.input file as well. In the job manager you can see I have run all the input parameter in the queue condition. Suppose when the SCF input has been finished, then band structure will automatically start the calculation. So you can wait until the calculation finished, and when the calculation finished, in this project window you can see their output file will be generated. So in the job manager you can see all the input calculation has been finished and their output has been generated. So you can see this is the band structure.xml file. So right click, select this show view. So you can see this is the band structure for this bismuth selenide without spin, and again you can select this band structure.xml file. So you can see this is the band structure of this bismuth selenide where general spin is included, and in this band structure you can see the spin orbit coupling calculation has a significant effect on the band structure, and that's make the band gap at the Z point larger. So however, we do not see any band crossing the Fermi levels. So this is the reason why bismuth selenide material is an insulator. So again, you can select this band structure.xml file where surface is included. So this is the band structure for this surface bismuth selenide, and this is the density of state.xml file. Right click, show view, and this is the density of state with respect to energy. So thank you for watching the video.